Okay, let's get back into actual material. Sometime. Let's get back into actual material. Okay, so what did we talk about before we were rudely interrupted by some midterm by some terrible professor? CFGs, but I think we were doing something else. But well, CFGs, but then we started something. Yeah, yeah. So PDAs. So I'm very familiar, obviously, with public displays of affection. So that's what these are, right? Yeah, obviously. So what do we know about PDAs? In this class, I mean. Yeah, a stack on what? So what does the stack mean? In relation to what? I can put stuff on a stack. Yeah, that's what a stack is. But what is the stack attached to? DFA, NFA. So we're putting the stack alongside the NFA. So is there a limit to how big the stack can be, or can I just keep putting things on the stack? I can put things on the stack. What if I limit the size of the stack? Stacks are getting expensive. Stacks can only have size at most 100. So does that change anything? Well, they're actually the same thing as regular languages if I limit the stack size. Here's what you do. Well, in each of the states that I could be in, I can have any set of stack contents at all. So just make a state for each one of them, and then make a transition for each. And then now I have just a simple DFA. So if I don't limit the stack height, then we can get non-regular languages. And in fact, we do. So what was the example that we did last time? Yeah. So we did 0 to the n, 1 to the n, and at least 0. Oh, here's another thing for the test, by the way. So if you put like the language A for that question 3 or whatever equal to 0 to the n, 1 to the n, is that a language? No, what is that? The thing on the right. Just a single string, okay? And also, what is n here? Right, so by putting it in curly brackets and saying n at least 0, now we have a language, okay? Just something to keep in mind. Okay, so we made these PDAs, and what do we want PDAs to be? More widespread, obviously, but what do we want PDAs to be? What did we do with DFAs and NFAs, and then we made the regular grammar thing? So are those equivalent, DFAs, NFAs, and regular grammar? Yeah, and how did we show that? Conversion. Yeah, so we made a conversion between a regular grammar, from a regular grammar to an NFA, and from an NFA to a regular grammar, to show that they're equivalent in power. I can convert one to the other. So if we want PDAs to be the model of computation for context-free languages, what do we better do? We better do a conversion between what and what? CFG and PDA. Because CFGs, we defined context-free languages as being the languages of CFGs. So if we show a conversion between the two, we're all set. Cool. So that's what we're going to at least start today. Okay, so our goal then, something to always keep in mind, the goal, is to show conversion from a CFG to a PDA, and from a PDA to a CFG. Looks like airports, right? like flights, going from one airport to the other. We're getting round trip tickets here. Okay, so we're actually gonna do the first one first, obviously, namely because it's the easier one of the two. So let's think about a CFG for a moment. So let's make a simple CFG. Let's do the prototypical one, 0S1 or empty. The famous non-regular language, 0 to the n, 1 to the n, and at least 0. Okay, well, let's see. So we have a grammar right here, and we want to make a PDA for it. Okay? Do we know how to make a PDA in a vacuum, ignoring this grammar? Do we know how to make a PDA for that language? 0 to the n, 1 to the n. Yeah, in fact, we did. So we pushed on that $ thing and then did the... In fact, I'm just going to redraw it here because it'll actually be useful. I'm not going to put state names because it won't actually matter here. So this is what we did last time. Oops, 0. So this is the machine that we actually did. So we pushed on this $ thing. As long as we see zeros, keep putting zeros on the stack. Whenever we encounter one, pop a corresponding 0 off the stack. And if everything's okay, we should see a $ on the bottom. Because we pushed that on at the beginning, because the stack started empty. Okay, cool. So what do we want from this? So remember the conversions we did before. So from an NFA to a regular grammar and back and forth. Do those work for any NFA and regular grammar? Yeah. So we want this to be algorithmic too. We want this to work for any CFG, because if it doesn't work for a particular CFG, I can't claim that they're the same. So it's got to work for any CFG. You guys have infinite amount of time to check every CFG to see if this works? If you do, you should contact me immediately. Okay, let's see. So we got to convert an arbitrary CFG into a PDA. Okay? Well, let's see. So what actually happens here? So the only thing we really have to go off of for our conversion thing is the grammar itself. That's the only thing we have to go off to make a PDA for it. So the only thing we really have are the rules of the grammar, right? Well, let's see. What does a CFG do? So let's just say we have this string in mind, an arbitrary string in mind. What does the grammar do? How do we get that string? What was that? It generates it. So we start where? Let's start variable, and then what do we do to eventually get that string? Yeah, substitution, apply rules. So I replace a variable with stuff, replace a variable with stuff, replace a variable with stuff, blah, 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 blah. Okay? And then eventually, what must there not exist in the derivation to get this string I want? A variable. A variable can't exist because I need to be able to replace it. So correspondingly, what does the PDA do? So what is a PDA given? Or a DFA, doesn't matter. A string as input, and then what happens? We read the string left to right. So the PDA reads strings left to right. Well, consider a derivation in the grammar. Go back to the derivation in the grammar. And suppose that we look at a leftmost derivation. What is a leftmost derivation? We replace the variable on the left, the leftmost variable. So let's just say that this A right here is the leftmost variable. Well, if it's the leftmost variable, what do we know on the left of A? It's only terminals. Will those ever be replaced? No, because it's a context-free grammar. Only variables are replaced. Well, what does that mean? That means that this front of the string will never change. This derivation part will never change because it's just terminals. Well, in PDA land, couldn't we just read those terminals because they'll never change? Well, if the grammar's after this string I'm trying to generate, and I want the PDA to be able to accept that same string to have the same language, well, couldn't I just read off those terminals on the front? And then once I get to a variable, then I do something there? Because those terminals never change. Well, if I get to a variable, now I have something to do. Well, let's see. Well, if I have a variable in a derivation, what must I do with it? I must apply a rule. Well, can I apply a rule with just states? Well, once I have a PDA, is there an operation to add a state? No, there's no operation like that. Shoot. You guys have other ideas?
Stack.
Oh, let's see. Could I put this derivation on the stack? So we just mentioned that the stack can grow arbitrarily big. So I can always put stuff on the stack if I need to. Well, we better be careful here because for a stack, we can only access the contents on the top. So in this derivation, if I'm reading characters that are generated by the grammar that'll never change, where must the top of the stack be? Should it be over here or over here? Well, if I'm reading characters left to right, where should the top of the stack be? On the left. Right. Left, correct.
Yeah.
That's what I meant. So if we just flip this on its side, then the short part, then the A is here, then the part that's just terminals, that's what we want. And if they're just terminals, they'll never change. So that must mean that for the PDA's perspective, when it's reading the string off the input, it must pop those same characters off of the stack in tandem. Okay? Well, what happens then? Let's just say we pop all the way down to A. So we have the variable A on the top of the stack now. So it's not a terminal, so I can't just read it off the input. It's just a variable. What do I do now? What do we do with a variable in a derivation? Apply a rule. Can I apply a rule on the stack? Well, if you see a variable here, well, is that variable going to be replaced after I apply this rule? Yes. So what should I do with the variable on the stack then? Pop it off. And then what do I replace it with? The right-hand side of a rule. Sounds pretty reasonable. Well, at the very end, what should there be on the stack? Well, let's see. If there's a terminal left, then I still have input to read. If there's a variable left, I still have a rule to apply. So then there should be nothing left on the stack. Do we have a check for empty stack operation? No, we do not. Shoot. You guys have other ideas?
Didn't we put an initial symbol in there that we just checked for?
Oh, look at this PDA right here. Does it have an idea that might be useful? Put a special symbol on, and then at the very end, pop that symbol off, and then go to a final state. This PDA is actually very useful. So let's actually do this. Do this grammar and derive the string 0011. So let's see. So here's our stack initially. So what does the stack always start as? Is there anything in the stack that, when I just turn on the PDA? No, there's nothing in the stack. It always starts empty. What do I put in there first? A special symbol, let's do $ again to keep with the theme. Well, let's see. Okay, so if we see a terminal, read it off the input, fine. If you see a variable, apply a rule to it, and then put the contents of the right-hand side on the stack. Great. Is either one of those situations true here? A variable or terminal on top of the stack? No. Oh, so we're stuck right at the very beginning. Is there something that a derivation always starts with? Start variable. Ah, so all derivations must start with a start variable, oddly enough. So what should we do with it on the stack? Put it on the stack. Exactly. So we still have our $ down here because we're rich. And let's just say that this S is the thing we want to push on. Non-$, sorry. We put the S on the stack because it's the start variable. Remember, whenever we're doing a conversion, we're always trying to simulate something with something else. We're trying to simulate the derivation on the stack itself. Derivations always start with the start variable, so we've got to put the start variable there. Okay, so now we have the S there, so we're all set. Great. So what do we do with this S now? There's a variable on top of the stack. What do we do? Pop it off. Perfect. So we pop this off, and then which rules should we apply? So $ still downstairs. So which rule should we apply first? The 0s11. So don't do what I'm about to do. Oops. I put the right-hand side on top of the stack. Is that what we want? Remember, how is the string being generated? The zeros are on the front. So where should the 0 appear? Well, first off, the 0s and the 1 must appear in different cells of the stack. So you can only have one thing per cell, first off. But where should the 0 appear? Should it appear on top or on the bottom? Because we're reading left to right on the top. So which order then, be careful, should we push things onto the stack? What order? Right to left, in backwards order. Okay, so the first thing we should push on is the 1. Good. So 1 is first, then S, then 0. Oh, so now what's on top of the stack? A terminal. So what do we do with terminals on top of the stack? Pop them and what do we do with the input? Read the same character. So we see a 0 on top of the stack, we pop it off and read it off the input at the same time. Because the string on the input's the thing we're after, so we better read it at the same time we generate that character on the stack using the derivation. Okay, so let's see. So the stack now is rather tall. So we have a 1 and an S. So the variable's on top now. So what rule should I apply next? The same rule again. So I'm going to have a stack now which has $. The 1 is still there, but I killed the S there. Sorry, S. Then I replace it with 1, then S, then 0. So notice, there are 2 1s on the stack. We will get to them, but we're not there yet. Okay, what's on top of the stack, a terminal or a variable? I should have more than one person answer. Terminal. So what do we do with terminals? Pop it and read it off the input. So pop that guy off, 0. Okay, so the stack now is, let's see, it's $, then 1, then 1, then S. What's on top of the stack now? Variable. Oh, which rule should I apply this time? Good, S goes to empty. So whenever we have a transition like this, we pop the variable S off always, but now we just replace it with nothing. We don't put anything on the stack, which is fine. So the stack contents are now $1 and then a 1. Oops. So just 2 ones now. So what do you think these ones are, what's going to happen with these ones?
When you apply the epsilon, do you read an epsilon at the same time?
Oh, so be careful. We're not actually reading anything there. We're just not reading. So in that case, since we're replacing a variable with something else, we're not actually reading there. So whenever we're replacing a variable with the right-hand side, we never read.
Okay.
So the only time we actually read, so good thing you brought this up, the only time we read is when we have a terminal on top. So whenever we have a terminal on top, then we read, but never any other time. So only at those times. Okay, so we have a 1 on the stack. We pop it off and read it off the input. Next stack contents are with a 1 on top. We pop it off again, and then read it off the input again. And then the only thing we have left is the $. And then what do we do at this point? Pop the $sign off. So we pop that guy off, and then we go to a final. So at this point, the stack, we should be in a final state at that point. Because we should accept at that point. Because we matched everything correctly. If we go to a final state and our stack is empty, and we haven't read all the input, will we accept? No, because the machine doesn't accept if you don't read the entire input. So we're actually fine here. If we somehow get there without reading the input, we're not going to accept anyway. So that's fine. Cool. So let's actually make a PDA for this thing. So I'm going to put the grammar down here again so that we can remind ourselves. So what is the very first thing that we should do? Get a beer after your class. No. I actually don't drink, but anyway. Let's see. So what do we do first? Yeah, put the $sign on. Do I read on this transition? No, because those only correspond to popping things off the stack. Should I read anything here? Well, same reason we don't do it there. So epsilon, epsilon, and then we push on $. Well, let's see. Well, what do we do next? What was our next step? Push the start variable on, which in this case is S. So here's actually one of the reasons why it's so nice to be able to put anything on the stack. So that's why we had a separate stack alphabet for PDAs, is that on the stack here we can put terminals and variables. So we can put anything on the stack we want, which is nice because we allow ourselves to do that. So on this transition, it's almost the same, except now we push on S instead of $. So this next state that we're going to, I'm going to call Q loop for reasons that we're about to get into. So think of this Q loop state as the central headquarters to figure out what is my next step. So when we go back to Q loop, we're going to figure out what's on top of the stack and figure out what to do at that point. Okay? So let's handle the terminal case first because those are easy. Well, actually, both of them are easy, but let's do the terminal. What if we see a 0 on the stack? What do we do? Of those 3 operations, what do we do? or read a 0, we're obviously going to pop a 0. Are we going to push anything? No. So in fact, and then once we do that, then we are going to figure out what to do after that. So that means we got to come back to Q loop immediately. So we're going to have 0, 0 goes to epsilon there. And I think for the same reason will apply for the 1s. So we'll have a transition 1, 1, epsilon. So I think that's pretty algorithmic. So whatever the terminals of the grammar are, just make a self loop on that terminal, popping that terminal, push nothing for every terminal in the grammar. And at the beginning, always push start the $sign on, then push the start variable on. Those are algorithmic. And then the same thing for the self loops. Okay, so now we gotta handle the case where we see the variable on the top. So tell me at a high level, if we see a variable on top, what do we do? Replace it with the right-hand side. In which order? The right to left. So like in the 0s1 case, we push the 1, then the s, then the 0. So there are many ways you can do this. I'm just going to show you one way. So the way I think of it is, think of the popping of the s as one operation, then the pushing of the right-hand side as a separate operation. So the way that I'm going to do it is, we're going to pop the s off and no pushes at all. Then we're going to push the right-hand side in order. So it's going to be in 2 stages, I guess. But I can't do that in one transition. So I'm going to do it in a whole suite of transitions. So the first transition, we're not going to read, pop the S off, and push nothing immediately. And I'm not going to name these states because there's just going to be a few of them, and we don't need to name them. And then after we pop the S off, then we're going to push the right-hand side in the backwards order. So we have 3 transitions then to do. So we then need to do the transition where we don't read, don't pop, and then push a 1 on, because we have to push the 1 first. Then we make one more transition, which is same thing, but now we're pushing on the S. And then one transition going back to Q loop with pushing on the 0. Okay? You see why it's called Q loop now? So you, whenever you do the rule translation to PDA land, you have these loops that go out from the state and come back to it. Okay, what about the S to epsilon rule? Well, what is the first thing we need to do if we see an S on the top, no matter what? Yeah, pop it off. So we're going to have a separate loop. So again, you can combine these possibly. I like keeping them in separate loops to keep everything straight. But I can see, like, to make the diagram easier, to combine them with the same transition from the previous loop. Either way is okay. This is just less error prone. So this one, we're going to do the same thing going out, but on the return trip, are we going to push anything back on for the S to epsilon rule? No. So in fact, we're going to have a triple epsilon transition, just like the earlier PDA example had. But you very well could have just made this epsilon S to epsilon rule be a self loop, because you don't really need another transition for it. Again, there are many ways to do this correctly, but just note that if we did it this way, it's completely algorithmic. So it can work in general. So if we do all this now, and we're done reading the string, what should be on the top of the stack? $sign. So we should then go to a final state and pop that guy off. Hope the NSA didn't hear that. Epsilon, then pop the $sign off, and then maybe push nothing, because I'm neat. And then go to a final state. Because at that point, we should accept. Okay, so what is the big idea? Put on something to detect that we're done, put the start variable on, then if a variable's on the top of the stack, apply one of the loops, which is applying a rule on the stack. If we generate a terminal, it's going to appear on top, and the only thing that you could ever do is doing the reading transitions. You can't do any of the other ones because those involve variables being popped off, and you can't apply those. So the only ones you can do are reading off the input. So if you generate a string, you're going to read the exact same string with the PDA. And so that's the entire conversion. So what you do in general is the four main states, the Q0, Q1, Q loop, and the final state, those are always there. Because think about it for any grammar. You're always going to put on the $sign. You're always going to put on the start symbol. And then you're going to always pop off the $sign on the end. If you have terminals, you're going to do the self loop, just reading and popping them off. And if you have rules, you're just going to have one set of transitions that goes out and comes back. Pops that variable off, and then pushes the right-hand side in reverse order.
So for each rule, will you have its own separate loop then?
Yeah, so that's the way that I would do it to keep things less error-prone. I would keep them as separate loops, but you very well could, in this case, combine the first transition out because they're exactly the same. And it doesn't actually matter there because only the top of the stack actually matters. So you could combine them, but it's more algorithmic to do it this way. But I can understand that the diagram could be horrible if you have too many rules. Other questions? Okay, so does this work in general? I said it's algorithmic. So it actually works in general. So that means that the languages of CFGs and PDAs are the same, right? No, what does this show? Every CFG can be recognized by a PDA. Could it be possible that a PDA has a non-context-free language?
Yes.
Yeah, it could be. It turns out it won't be. But from what we know so far, it could be. So what should we do next? And we're definitely not going to do it in 10 minutes. I'll just highlight it for the next 10 minutes then. Yeah, we got to convert an arbitrary PDA to an equivalent CFG. That would be our goal. Well, all PDAs definitely have this form, right? No. If they did, that would be easy. We would just do the construction in reverse, but we can't. And in fact, a PDA could pop on its first transition. So here's the thing. Here's actually an interesting exam question. It won't be because I'm now asking it. Suppose that we have a start state for a PDA here, and the first transition, or all of its first transitions, all of them pop. What is the language of that PDA? If it pops on the first transition, could we even apply those transitions? No, because the stack starts empty. I can't apply a transition that pops first because the stack is empty. So what are the languages that PDA could be? Well, it could be empty because the start state could be nothing. It could be a non-final state, or it could be what? So let's actually do this, because a lot of you look confused. So let's just say that we have a transition. It doesn't matter if we read, but we pop and then maybe push. But which of those two operations occurs first, the pop or the push? The pop occurs first because of our reasoning earlier. So can I apply this transition here? No, I can't. So we might as well just assume that these transitions don't exist. So what are the possible languages of this PDA? Well, what is the language of this PDA? Empty. Empty, because it accepts nothing. Well, could this start state be final? Yeah, so what is the language of this PDA? Empty string. That's the only string I can accept. Can I accept any string of non-zero length? No, because then I can't apply a transition. So we could have stupid PDAs that just pop on their first transition. And we don't have to have anything sensible. So we got to think more carefully about this, because we can have a PDA of arbitrary structure. We gotta be able to convert a PDA with states that can have any form into a grammar that has variables, rules, and terminals and all that jazz. So what do we actually do? Well, could we get it closer to this form to make it a little bit easier? Well, we can't, obviously, because not all PDAs are like this. But could we get closer? Well, let's see. Could a PDA have two final states? Or two or more final states? Yeah. Well, here's a quick claim that's actually pretty easy to prove. So every PDA has an equivalent one with exactly one final state. Is that true? I don't want to just say, oh, this is a claim, therefore it is true. I want you to verify it for yourself. And that's kind of like a life lesson. If you hear someone say, oh, this is true, what should you do?
Verify.
So there's a 3-word phrase that's actually that I strongly adhere to. Trust, but verify. So you should trust me in believing this, but verify it for yourself. Is this actually true? I mean, you could prove it by contradiction, but there's a much easier way. What would you do with, like, say, an NFA? Ignore the stack. Yeah. So what you would do is you would take the NFA, I'll convert it to a PDA shortly, and you would just make epsilon transitions to a single final state and then make the old final states no longer final. It's kind of what you would do with concatenation. And in fact, it kind of is concatenation. If you just treat it as a single state NFA. Well, how would I translate this over to PDA land? Should be an amusement park. What would you do to the transitions? Well, yeah, well, we'll do that. But does the stack have to end empty? No. So no matter what the stack is, if I do nothing to it going over to this new final state, am I still okay?
Yes.
Yeah. In fact, we're still okay. Annie, are you okay? Okay. Horrible song references by Ryan. Okay, so this would work because now if the box is a PDA, now we have a PDA with exactly one final state. Pretty cool. Well, let's see. We got to have exactly one start variable, right? We got to have a start variable, and what is the job of the start variable in the grammar that we're going to make? It's to generate all the strings that this PDA accepts, right? So let's see. We got to have a variable, the start variable, that says these are all the strings that take me from the start state going to that single final state. Okay? Well, let's actually So we got to have a variable that represents all strings going from start state to the only final state. Because that's what the language of the PDA is, because it has exactly one final state. Pretty cool. So we got to go from the start state to a single final state. Well, consider this situation, and then I'll let you go. So consider this situation. Let's say that this is the start state on the left, and here's that single final state on the right. And let's look at an intermediary state in the middle. And suppose that we take a lot of transitions to go to that middle state, and then the middle state takes a lot of transitions to go to that final state at the very end. So this is just an arbitrary state in the middle. Well, if I knew all the strings that took me from that start state to that middle state, and I know all the strings that take me from that middle state to the final one, how do I represent the strings that take me from the start to the end? A concatenation. So if I know how to get to some place in the middle, and then from that same middle place to the end, we just concatenate them. So think of this like merge sort, for example. If I can sort these two halves of the list, what do we do with the two pieces? We join them together. So think of this like we're solving a bunch of sub-problems and then combining all of the solutions together to get a solution for the overall problem. Okay, so I'll let you think about that, and then we'll get back to it tomorrow.